Hello everyone, and welcome to Smart Team's final presentation on heartbeat-based authentication in wearable devices. During the COVID-19 pandemic, quarantining of people who potentially have COVID-19 has been a strategy used to stop the spread of the virus. For example, a traveler from an overseas country with a high amount of cases may be asked to quarantine at home to prevent a potential COVID-19 outbreak from occurring. For home quarantine to work, the person under home quarantine must stay in their house for a certain number of days. However, it has been found that not everyone who is under home quarantine has been at home when checked. A solution to this is a device to track the person to ensure they stay at home. But how do you know who is wearing the device? This is where heartbeat-based authentication comes in. Our project involves collecting a heartbeat sample from a user and analyzing it to authenticate that they are the right person who should be wearing the device. Our project uses a sensor tag as the wearable device and an SVM model to authenticate the user. To complete this project, we have split it up into a number of tasks, which we will describe in this presentation. These tasks are the collection of the heartbeat using the sensor tag, including sending it back to the PC, segmentation of the collected sample into heartbeats, extracting features from these heartbeats, and then inputting these extracted features into an SVM to train and authenticate a user. After this is evaluation, where we will evaluate the accuracy and effectiveness of the system. I'll now pass on to Nick to talk about collection.
The collection onto the sensor tag from a user's perspective would be they pick up the device, they hold it against their chest, they would push the left button, they would hear a tone. After 8 seconds, they would hear another tone, letting them know the sensor has finished taking readings. Then on a client computer, we would download the readings using a small Python script. This small task faced many challenges. Two core components of them were the physical taking the reading on the device, and then the transmission of that reading on to the client PC. The collection onto the device, we found our first challenge was finding out how to take the reading. The MPU 925 accelerometer, the driver being built with Kentucky, actually did a fair bit of casting, so you'd lose a significant amount of precision as it went from an unsigned integer to a floating point number back to a signed integer. So we altered the code and built our own version of Intidi with a slightly different driver. Other challenges we faced is because we needed to make samples of 250 per second. This excluded the use of C and E timers, as they only allow at most 100 samples per second. But from the literature, we knew we needed upwards of 150, 200, 250 was our objective. So this meant we had to use R timers. From the literature, we knew we needed upwards of 150, 200, 250 was our objective. So this meant we had to use R timers. The physical space on the driver only allowed us to store originally 3 seconds if we were using all 3 axes. Once we trimmed down to the Z axis, we were able to take an 8-second sample, which was enough for a good 6-7 heartbeats, which was enough for the SVM to work. Other challenges we faced with the collection was when we started messing with R timers during the reading, it would actually completely kill the RF functionality of the sensor tag. So it took us a long time to find out that the 6-low pan would just stop working when we took a reading. We got around this by cycling the RF functionality using code similar to that sends it into a hibernation state. So simply by sending a command to turn off the RF and then back on, we're able to restore functionality. So after each sensor reading, the RF functions are cycled. The networking physical layer, we originally tried to use Bluetooth, and we did a lot of experimentation the original path was using a fork of Kentucky called Kentucky MG, which is a maintained version. It has a Bluetooth, experimental Bluetooth driver for the sensor tag. But it's more a mesh network, and we weren't able to get it working to our level of satisfaction. And how it's implemented in the new version of Kentucky or Kentucky NG is it still requires an edge router. The other option was to use Texas Instruments' own real-time operating system. I was able to build that onto the device, but it would have required learning another real-time operating system, and due to time restraints, we didn't pursue that path. We actually just fell back to the 6LoWPAN, given that we're able to reuse functionalities for sending TCP packets back and forth. There was a fair bit of debugging, as I spoke about earlier, in that the RF would drop off, but once we moved past that, we were able to send TCP packets to a client script running with Python scripting. How that worked was we would create a sort of application network where the 8,000 readings were split in 2,000 readings, 250 for 8 seconds, were 16 bytes. We split them into two 8 bytes. Each of those 4,000 bytes were then factored into 500 long chunks that we'll refer to as frames. Every one of those frames has a single byte added to the start, giving it its order. So the first frame would be a single byte front with 1, then the 5,000 readings, or 500 bytes, which correspond to 250 readings. The Python script running on the VM with an edge router would send 4 chars corresponding to send. Kentucky would read this, it would start sending the packets back to the Python script. It took a lot of debugging because we found that the TCP implemented in Kentucky is not quite true TCP in that acknowledgements aren't actually referenced back to the correct packet. So what we did was the Python script would just leave its socket open for 3 seconds, and even though the TCP packet was fragmented, we're not sure if that was by Kentucky, by the edge router, by something in the path, into about 64 bytes, and we just wait 3 seconds for it to all come in, check there was the 501 bytes, check that the first byte was the expected frame number, then send. The Python script asked for the next frame. And we were fairly successful. We're able to send a full 4 kilobytes back in about 15 seconds, which isn't fantastic, but is what it is. Once the Python script had received the 4,000 bytes, it would then check each of the frames, drop those single bits from the first bit part of the frame, and then with those 4,000 bytes, take every 2 and merge them back together into unsigned bits, and then output them to a CSV, which was then fed into the SVM.
Thank you, Nick. So now I'm going to talk about heartbeat segmentation. As the sensor tag collects heartbeats in a continuous manner, we have to separate it into different individual heartbeats. Since an average person has a heartbeats ranging from 50 BPM to 120 BPM, we divide the collected heartbeats into sections of 2 seconds to guarantee that at least one full heartbeat cycle can be collected in each section. We then try to segmentate out the heartbeats in a section. The heartbeat cycle contains features such as AO and RF. These features can be found to correctly segmentate the heartbeats pattern. In each 2-second interval, we will extract a single heartbeat. We do this by identifying the AO and RF using the shortest distance between 2 peaks that's greater than 200 ms starting from the highest peak. This performs well in trying to find the AO and RF, as AO to RF intervals are larger than 200 ms when the heart rate is lower than 120 bpm. Now that we have obtained the AO to RF distance, we simply multiply 0.5 to it to obtain the ATC to AO distance, and from that we can obtain a full heartbeat cycle. After heartbeat segmentation, the next task was to convert the segmented heartbeats into features appropriate to be used in training the SVM. The feature extraction process needs to retain the characteristic of the user's heartbeats while removing irrelevant noises. The paper outlined numerous methods of feature extraction. Our team tried the following three. The first method was the average of AO, RF, and ATC. This was implemented by taking the average amplitude of all heartbeats during the different stages of a heartbeat cycle, namely the average ATC, AO, and RF. The resulted SVM did not perform as well as expected. Clearly, traditional methods of extracting features based on the interval between different heartbeat stages is not applicable in our situation. This is due to the variation in amplitude of SCG, leading to unreliable heartbeat stage identifications. Therefore, we switched to using discrete wavelet transform, DWT, to extract features from the SCG signals. The DWT decomposes SCG signals into 5 levels, with level 1 to 5 represents signal components in the frequency range of 25 to 50 Hz, 12.5 to 25 Hz, 6.25 to 12.5 Hz, 3.13 to 6.25 Hz, and 1.56 to 3.13 Hz. To reduce noise in SCG signal, we only use detail coefficients from the second level to the fourth level as the feature factor for the heartbeat's authentication. From here, we tried using the average of the detail coefficients across these 3 levels, but resulted in an even lower accuracy than the first method. It came to the team's attention that more features are required to improve the model. Hence, we ended up using all values across these 3 levels to obtain a 56-dimensional feature vector, which resulted in an improvement in the accuracy. I'll now pass it to Nathan.
I'll now talk about the SVM training as well as authentication. For this project, our team used the SVM implementation provided by sklearn. We also used a pandas data frame to store all data and then pass this data frame into the SVM as its input. As you can see in this diagram, to train the SVM, we firstly had a database of heartbeats. These heartbeats were of the negative case and were necessary to train the SVM to distinguish between the correct and incorrect heartbeats. These heartbeats underwent segmentation and feature extraction as has been described before being stored in a data frame. Now, when training, the user will input their heartbeat as the positive case. Their heartbeat will undergo the same segmentation and feature extraction, and then will be appended to the data frame, which is already full of the other heartbeats, to form a single data frame. This data frame is then inputted into the SVM so the model can be fitted. Now on to SVM authentication. So authentication is very similar to training, except it's a little bit simpler. So the user will input their heartbeat just as they did in training, and the heartbeat will undergo the same segmentation and feature extraction. This heartbeat is then put into a data frame, and then we can use the SVM model's method called predict with the argument of that data frame, and then the SVM model will predict whether it thinks this case is of the positive or negative class and give its prediction. I will now show you how you take a heartbeat reading. So as you can see in this video, you take the sensor tag and place it against your chest. You then press the left button and the sensor tag will buzz, indicating that the heartbeat reading has started. You then wait till the next buzz, which indicates that the heartbeat reading has stopped, where you can take the sensor tag off your chest. I will now do a quick demo of our system. So running main.py, we have 4 options. The first option is generate training data. So this corresponds to what I was talking about in the SVM training slide about the heartbeat database. So we have a collection of heartbeats. Generate training data will turn those heartbeats into a data frame which is exported to a CSV. This CSV can be imported later as a data frame to be used for training. So running that will give a CSV of our training data. So option 2 is train. This corresponds to the second part of the SVM training slide, where the user inputs their heartbeat pattern and is appended to the existing data frame of the negative heartbeats, and the user's heartbeat is added as a positive case. So this is where we would be prompted to add our heartbeat, and then after it's added, we train. And now the SVM is trained, and here you can see the total data frame that is created. So with predict, we need to give our heartbeat to the system, and then it will use the predict method from the SVM model to tell you if you're successfully authenticated or not. So as before, we would add our heartbeat here, and then we would go 3 predict, and here you can see a returns 1, which means we have been successfully authenticated by the system. On now to evaluation. So for evaluation, we use 5-fold cross-validation to evaluate the accuracy of the SVM model on each of the 3 feature extraction methods described before. We use the cross-validation method from sklearn. You can see the accuracies on the table in the slide. So for the first method of averaging the AO, RF and ATC scores, that gave 71% accuracy. Averaging the DWT values across 3 levels gave 65% accuracy, and using the full DWT array across 3 levels gave 76% accuracy. So the highest accuracy was option 3, using the full array. So therefore this method was chosen as our final method. With an accuracy of 76%, this system needs improvements before it can be used for authentication, as this accuracy is too low to protect the system against attackers, and also deny legitimate users at a rate too high. An accuracy closer to 95% would be appropriate before the system can be used for authentication. So, to summarize, in our presentation, we have demonstrated our implementation of using heartbeat patterns for authentication. Our results have demonstrated that heartbeat-based authentication is possible, and with some improvements to our system, such as more heartbeat data and a more fine-tuned SVM model, we believe that our heartbeat-based authentication system can be used for any authentication applications, such as tracking and authenticating that a person remains in home quarantine during the COVID-19 pandemic. And that concludes our presentation. Thank you for listening.